So the first one that we just walked through, so this is my typed up answer. Partial x converted to polar, partial y converted to polar. I went ahead and converted to polar first, put them in there, and then you factor out a 4, and cosine squared plus sine squared is 1, so you get 1 plus 4, which is worth 5. And then your RD theta. Integrate with respect to r, plug in the 2 minus plug in the 0, integrate with respect to theta, and you end up with 4 pi root 5. So beautiful, beautiful. Okay. Did you guys get number 1? Yes, you did. Good. 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 Yeah. All right. Every single group got 4 pi root 5. So well done. So the second one, I let you use calculators. I was more concerned with the setup than the calculation. Find the center of mass of the lamina bounded by y equals 6 minus 1/2 x minus 1/4 x squared in the first quadrant if your density is just equal to k. So first you find the mass, which is just the double integral of the density. Then you find your m sub x, m sub y, and then your final center of mass is just m sub y over m and m sub x over m. So if you're, let's see, so the hard part is producing the double integral that gives you the area bounded by this guy in the first quadrant, but this one's actually not bad. So I don't think I have the graph on here. The graph, which I saw on a lot of your boards, it's this upside down parabola, looks like this. So since you have a calculator, you just use your calculator to find this x value. And then your y's are just going from 0 to your function, and your x's are going from 0 to whatever that x value is. Okay. So anyway, it ends up being 4. Oh, that's nice. Okay. So I have, for my mass, 0 to 4, 0 to the function of k dy dx, and I got 44 thirds k. And then for my m sub y, I get 64 thirds k, and for my m sub x, I get 496 15ths k. So my final center of mass, when you divide, is 16 elevenths and 124 55ths. Beautiful, beautiful. Let's see, that reduces, yep.
You know what no explanation that produces to? Is that correct?
Oh, there we go. See it. Okay, yeah, beautiful, good. So it looks like we're all doing fairly well, even though we're complaining a lot about how to do these. At least one person in every group has some idea of what to do, so that's good. All right, find the volume of the solid bounded on top by z equals sine y plus 3, and on the bottom by a triangle in the xy plane with the corners at -1, 1, 0, -2, and 3, 4. So I tried to, I was explaining to a couple of students, I don't want to name names, but yeah, I guess it really doesn't matter. So I was explaining to Lily how, I don't know, does it feel like I'm putting you on the spot if I say that? So anyway, so I was trying to explain how volume is calculated. So the thing that I don't know if we get, that I thought we got, but I don't know if we get, is whenever you're doing volume with double integrals, right? The actual double integrals, the limits of the integrals, those two integrals with their limits that you have an x and you have a y regardless of order, those two integrals are producing a region in the xy plane. It's a flat two-dimensional region, some shape in the xy plane. In this case, it's a triangle. Could be some sort of a squiggly thing, right? Whatever. But anyway, it's some shape in the xy plane. The z function is your height, right? So z is like floating around up here, right? So your z function is up above the xy, or it could be below, right? Or it could cross through. But most of the time, we're kind and we let it just all be above the xy plane, right? So what does the shape on the bottom do? The shape on the bottom the shape that is on the xy plane, in this case it's a triangle, that's the set of all the ordered pairs that you are plugging into your z function to get the height at each of those ordered pairs inside of that shape. And if you add all those heights together, you get volume. So what happens is they bound, those form like the outer boundaries of your region, and the z is just the height. So you end up with a region that has some sort of sides shaped by the region, this flat region in the xy plane, whatever it happens to be, and then it comes up to whatever your z function is. Okay? That's volume by double integral. Oh, yes?
So for surface area, would it be like that same shape, but just the surface area?
So for surface area, it's the same thing. You get a boundary, but when you do that square root of 1 plus f sub x squared plus f sub y squared, you're not finding volume anymore. You're just finding the area of the surface on top. Yeah.
Only on top of the z function?
Correct. Correct. It's bounded by your xy shape, right? But it's the actual z function inside of those boundaries. Yes?
If the z function is underneath, you have to do anything
No. But you'll end up with a negative answer. Right? Well, it depends. Like we're doing all of these with just one z function. Do you guys remember last year when you first learned area? And we were telling you area is just the integral of f of x, right? And then we'd say, well, really that produces the area between your function and the x-axis, right? And then later on you learned how to find area between two functions, and it was like some top function minus some bottom function. Does that not ring a bell? So if you had function f and function g, right? And I want the area from a to b, right? It's the integral of f minus g, right? Okay. So then I don't know if you were like how you were taught this, but I always said so if g is just 0, right? Then you just have the area between f and the x-axis because it's f minus 0, right? So here what we're doing is basically z minus 0. So your height is just whatever your z value is, right? Coming up. If it's positive, it's positive. If it's negative, it's negative. So technically, if we're asked to find volume, you would have to, if you had part positive, part negative, you'd have to split it into, yeah, no, I won't ask you to do that. So anyway, but yeah, because otherwise you get like a net volume, you get some positive, some negative, and it's just kind of silly, right? So anyway, so you want it all above or all below when you're doing your volume kind of thing. Oh, and if it's in between two z functions, right? So say I have some surface and then another surface, and I want the volume of the stuff in between, everything stays the same. It's just that my integrand now is the top z minus the bottom z, right? Because all that integrand does is it tells you how high to go, right? And so the xy integrals, the double integrals with the limits, those tell you what points to plug in, and then the z tells you for that point how high, what's your height, right? So whatever the height is, you add them together for all infinitely many points, and you get this volume. Does that help? I don't know if that helps. You guys probably already knew that. Do you all understand that? Okay, let's talk about the third problem. Let's just walk through it slowly. Okay. So Curtis, you got it. You got, yes you did. Yes you did.
I mean, I didn't get the answer for it.
Yeah, but you got it.
Oh, I did?
Yes you did.
Oh, I did?
You did.
Oh.
Negative 1, 1, 0, negative 2, 3, 4. Yes, you did.
Who got it?
He
Not
did.
me. Couldn't be me. I'm confused. Well, that's good.
All right. So whenever I'm doing these problems personally, it helps me to graph the region in the xy plane, right? You don't have to, but for me it helps. So negative 1, 1, 0, negative 2, and 3, 4. So I get this triangle. This is the triangle. These are the boundaries. Like if you think flat, like you'd have to take this and put it on the floor. Those are the boundaries, and then my z function is floating over the top. And we know that the z function never intersects the xy plane because it's sine y plus 3. The lowest sine y can possibly be is what? -1. So, right, so plus 3, you're always positive. So this guy's always above the xy plane. So we don't have to worry about the z coming down and intersecting. It's always just floating above. All right, so how do we write this region in a double integral? Well, it's just like when you did area last year. You're either going to do top minus bottom or right minus left. Either way, you're going to have to split it up. So I'm going to do top minus bottom because that's my go-to. I like top minus bottom. So I like dy dx. So if it's a potato, I'm going to go dy dx. So the slope of this line, so -1, 1 to 3, 4. So up 3 over 4, so y equals 3/4 x plus 2. And I'm just going to cheat and make sure that that's what, is that what you guys got?
It's 7/4.
Oh, it's not 2?
It's not 2.
Ah,
See, I was wrong.
okay.
Am I surprised? I'm not surprised. Yeah, you're right.
Okay, 7/4.
Wow.
All right. Okay, so y equals 3/4 x plus 7/4. And then this guy, so I'm cheating. All right, this is -3x minus 2. And this guy, this is 2x minus 2. All right, I'm cheating. Are your equations right? Okay, without having to do all the work of slope and intercept and everything. Okay, so for me personally, I would split this way and say, all right, so my first integral is going to go from x equals -1 to x equals 0, y equals -3x minus 2 to y equals 3/4 x plus 7/4 of whatever my z function is. My second integral would be x equals 0 to x equals 3, and then y equals 2x minus 2 to y equals 3/4 x plus 7/4 of whatever my z function is. Yes, Tish.
Sorry, but wouldn't you have to only do it like from the x equals or y equals 0 line and then above that? Because didn't you say that it would only have to be positive?
What would
The
I
z function.
The z, okay, again, this is the xy plane. You got to think of this as on the floor.
Oh.
Z is not on this picture in any way, shape, or form. You and I have had this talk before. You're not graphing Z. You're graphing X and Y, right? Z comes out of the board. Z, like if you're going to think Z, you got to think of it as out here. Not literally physically up or down or left or right. It's out. It's a third dimension. Yeah. All right. So, -1, 0. Let's see if we match. We do. Yeah, looks gorgeous. And I got an answer of 25.2. All right. So talk to me about questions. I'm going to give you some more today. After the lesson. There's actually some in the lesson too. Although today is our first day of
Triple.
da-da-da-da.
I called it.
Oh my god.
Are you serious?
Okay, so this is like 4 dimensions family, right?
It can be.
There's no way this out. Like, how is it applied to anything we're gonna do? Like,
You're gonna love it.
Like, what's past volume? Super volume? Like, what do you do? Everything.
Yeah, what does ever apply to?
So if you have, because you can have functions, okay, if you're thinking only in terms of space and volume, then this triple integrals will give you volume if there's no integrand at all, right? Because then you're still in 3 dimensions. As soon as you introduce an integrand, now you're right, you're in 4 dimensions, which physically there isn't any way to describe it. However, you can certainly have a function with 4 input variables, right? Like, so if we have a function Like we did one with, we talked about like product cost or something, right? And so if you're doing something to do with product cost, you might have the cost of materials and the cost of labor and the cost of renting this space and the cost of, I don't know, like advertising or whatever, right? You have like all these different costs. Each one of those would be its own variable, and you now have a function with 4 variables, right? Or more variables. So if you're wanting to do an integral for total cost, you can use integrals to find that kind of stuff. So you don't have to think, not everything is just talking about volumes in space, right? Yes, Dorsa?
For the second running target. Alright,
Oh, we're not doing the second part. Sorry. We did that the other day. Take that up. Yeah.
No,
Oh, okay.
My notes, they're all ruined.
Why are your notes ruined?
I wrote triple variables because I kept hearing variables instead of writing integrals.
Bro, I see your raise.
Just throw it away.
Erase?
I kept writing it then. Oh, notes are ruined.
Just, okay, honestly, personally, I think this is a moment of personal growth.
Oh my god.
Can you move forward from this, right? Cross it off, write the correct word, and move on.
Or leaving the variables as variables is really wrong.
Yeah. You can do this.
It's gonna look so bad though. It's not gonna matter.
You're the only one that's gonna
No
see
one
it.
on earth is going to know but you.
But now everyone knows.
Yeah.
Oh my goodness. Tajosh, if this bothers you this much, why are you taking notes in pen?
Yeah.
It's so much neat. Like, it looks so neat if I take notes in pen and you pencil combined.
Oh my goodness. Alright.
Yeah,
Are
white
you
out.
going to post it though on top if she's happy or just like find the new fancy notes?
Alright.
Just throw it all away.
So, our focus today is still going to be on volume. Mostly it's just going to be on can I evaluate a triple integral, right? But we're still going to focus on volume. Triple integrals, when you're finding volume with triple integrals, all you're doing is taking the z's from the integrand and moving them onto as the limits of an integral. It's like actually super easy. It's just saying x goes from here to here, y goes from here to here, z goes from here to here. Done, right? So, but if you think visually, I don't know if you guys remember when I first taught you volume with double integrals, what we did was I gave you this visual with all these like rectangular prisms sticking up, right? And so what you got, and I made you guys do it by hand, right? So you had to approximate the volume of under a surface by finding like the little area of the square and then the height and finding the volume of the little rectangular prism, and you add them all together and you get your volume, right? So now when you do volume with triple integrals, you're not doing a height like that. So instead, what you're doing is your delta x approaches 0, that narrows you in this way. Your delta y approaches 0, that narrows you in this way. Normally you would be around, that centers you around some little point, and in the past we plugged that in to get a z. Add them all, it's basically like a height with no area, with no volume, all these little skinny teeny heights, right? You add them all together. Well now, instead of just the x going to 0 and the delta x going to 0 and the delta y going to 0, we have an ordered triple. Delta x, delta y, delta z, all three of them kind of close in around a dot, and then you take all the dots in the entire space, add them all together, and you get the volume of the space. So essentially what it's doing is, so your x's get squished, your y's get squished, your z's get squished, and you get these trillion little individual cubes, these little teeny tiny cubes, and you're taking like the limit as this approaches 0, this approaches 0, this approaches 0, and you end up with these essentially infinitely many dots that fill the whole space, You add them all together and you get the volume. So it's kind of neat, right? It makes me think of Hubert.
Oh, it does.
Yeah. See? I knew that would connect. All right.
You know, Hubert, it's this like old arcade
It's an
game.
old
Like,
video
arcade
game.
Blocking, and he's like,
And he jumps from block to block to block to block. Yeah.
Hubert.
Okay.
He swears at everything he says. It's
Yeah,
like,
but he's not a. He just goes wrum, wrum, right?
Yeah.
Anyway,
They're all swear words, but like not really.
it's
Oh,
just
like
like
the
little
sign.
phrases that are made up of all the symbols on it,
Yeah.
like a pound sign and an exclamation point and a squiggle, right?
It's like old school
Yeah.
swearing.
Yes, Si. Quiet, please. Yes. Okay. The question was, why can't you just do a double integral? You can just do a double integral, right? But what we're gonna, all we've been able to do with double integrals is find a volume with a specific boundary, flat, that goes up to a z. Now we're going to be able to find a volume in any direction of any space we want. And so what we're going to do, we're going to start with rectangular. We're going to expand to a different type of coordinate system called cylindrical coordinates. And then we're going to expand to learn a different type of coordinate system called spherical coordinates. And between all three different systems, we're going to be able to find some really crazy volumes. It's going to be like really fun. Okay. Yes, Sophie. It's gonna, yeah, I mean, honestly, it's very similar to doing it with double. But you will start to get so used to using triple that, like, it's gonna be like, oh, double, it's been a while. Like, you'll get to that point where you're like, whoa, it's been a while since we've done double. Because I think you will build up a comfort level with triple. Okay. All right, so anyway. All right. With no instruction. I am giving you no instruction at all. Let's see if you can evaluate this triple integral. Yes, you can.
You know what? I'm just gonna wait. I'm just gonna wait. I don't miss this.
Now, first step, you're integrating with respect to z, right? So you have e to the x y z plus e to the x times 2 times 1 half z squared, so just z squared. So you end up with e to the x times yz plus z squared. From 0 to x plus y, plug in the x plus y's, you get this beautiful, nice, big polynomial, right? So personally, I would combine like terms before moving forward. Okay. Are we good with the very first integral? Any questions? We're all okay? Okay. Now we're going to integrate with respect to y. So now when we integrate with respect to y, you can just keep the e to the x out front. So you have 2/3 y cubed plus 3/2 xy squared plus x squared y. We're going from 0 to x, so now all of your y's become x's. I kind of want to not show that yet. But... All right. So what ends up happening once you plug in x's for all of your y's and you clean it up, you end up with 19/6 times e to the x times x cubed. How do we anti-differentiate an e times a polynomial? What method? Tab. So in case you've forgotten tab method, now I don't know why I put the 19/6 in with it. You really don't have to. But apparently that's where my head was at the time. So, can I move this? I gotta move the whole thing. Okay. All right. So, remember your u is the polynomial part, so you differentiate down. Your dv, that's the e part. You could be an e, a sine, or a cosine. You integrate down, and then your signs alternate plus, minus, plus, minus, plus. When you're writing out your answer, you go diagonally down. In this case, it doesn't matter, but it might in the future. So you go diagonally down. Do you guys remember tab?
Yes.
Zach, you remember tab? A little? Okay. Tab is what? Yeah. But then it's like, yeah. I like tab. Tab is something that sticks. All right. So So when you do your tab, you end up with, and you could have put the 19.6 in front and have totally different coefficients, which is probably the wisest thing to do. But anyway, I didn't. So you end up with something like this. Plug in the 2 minus plug in the 0. And your final answer is 19/3 e squared plus 19, or something equivalent. Now, the main point here was, can you do a triple integral? It's just like doing a double integral, except now you do a z, a y, and an x, not just a y and an x. Talk to me. Are there any questions, concerns, problems, complaints? Nick, how you doing?
Good.
Pretty good? Good. Hi, Ryan. How are you doing? Did you get the first part?
Yeah.
Okay. Did you get the next part? You're just starting over. All right. Danny, how you doing? Good? All right, we're going to use triple integrals to find volume. I am going to do this with you. I am going to walk you through it. It is not scary. Okay? Are we ready? You can do this.
Can we forget this unit ever exists?
You know what's fun? This is honestly, like, without question, this is my favorite unit. And I feel bad that I'm not doing a good job leading you through it. But
This is like the volume unit of last year. Everyone hated it last year.
really, that's my favorite unit from A, B, and BC too. Well, series. I love series too.
Oh, someone's
Yeah. Yeah. Okay. So we're going to use triple integrals to find the volume of the ellipsoid given by 4x x squared plus 4y squared plus z squared equals 16. Now, before we start, let's do something to make our lives a little bit easier. What is the center of this ellipsoid? It is 0, 0, 0. Right? How do you know it's 0, 0, 0?
Because there's no like thing inside the parentheses with the square.
Yeah, exactly. You're exactly right. Yeah, so there was... Okay, so if you guys remember from when you did conic sections back in Algebra 2 or whatever, when you just have an ellipse, regardless of an ellipsoid, but pretend there's a z, just an x and a y, if the center wasn't 0, 0, you would have an x minus h squared and a y minus k squared, and hk would be your center, right? So the same thing here. You would have some sort of parentheses of x plus number or minus number squared, and y minus number squared, or z minus number squared. Since it's just x squared, y squared, z squared, this thing is centered at the origin. Now, it's an ellipsoid, which means it has symmetry. And the x and the y are both going out by a factor of 4. The z is going up and down. But it's, even though it's not 4, it doesn't matter because there's still symmetry amongst the octants. So, because this lovely ellipsoid is symmetric amongst the octants, we can actually take the volume just in the first octant and then multiply it by what? 8. 8. There are 8 octants, right? So we're going to take the volume in the first octant and multiply it by 8. So how do we find the shape that we need in the first octant? So in the first, let's see if I can draw 3D. If I can't, it's okay. So I'm not, you know what, maybe I should. I was going to say, you have like this, your x and y boundary, and then your z boundary, right, coming down. At first I thought I was doing so well. Anyway, so like if you were to draw the whole thing, right, you'd have to be going out that way and backward and forward, but I don't want to get too complicated because then it gets all messy. All right, so anyway, all right, so, okay, that's the xy plane. That's the bottom of this octant's surface. And then, so what we have to figure out is, first, let's do our z's. We're going from 0, because the xy plane has a z of 0, and we're coming up and just hitting the z function. So we need a z function in the first octant, right? So the first thing that we're going to do is solve this guy for z. So normally it'd be plus or minus, but since we're just doing first octant, we're just going to have the positive. So it'd be z is the positive square root of 16 minus 4x squared minus 4y squared. We're not going to do any polar today. We're sticking with rectangular. We will deal with polar later. So does everyone understand that our z's are going to go from 0 to that function, because that gives us like the outer z shell, like that's for each z. Okay. All right. Now our x's and y's are still the x's and y's that produce that shape. So our y is going to go from 0 out to this function, and our x's are just going to be numbers. So to get our y, how do we find this function right here? Well, that function would be where our ellipsoid intersects the xy plane. What do we know about where the ellipsoid intersects the x?
Z is
0. So you set your z equal to 0, and you solve for, I'm going to solve for y. So set your z, I'm going to do it from here. Set your z equal to 0. So now, again, you get a plus or minus, but we're all in the first octant, so everything's positive, so you just put the plot positive. So y is the square root of 16 minus 4x squared over 4. Whoops, this whole thing. There we go. So, which equals the square root of 4 minus x squared. There we go. All right. So there's my y. So my y is going to go from 0 to this. Now I need to find my x values. So my x values are going to start at 0. Oh, you know what? I was going y this way. Why should we be going this way? That's our y. X is going to go from 0 to, I need this x value right here. Well, that x value, that's where the graph intersects the x-axis, which means what's 0 here? Y. Z and y are both 0 on the x-axis. So now to find your x, your numbers for x, set both of these equal to 0. You get x squared equals 4, so x is plus or minus 2, so it's just the 2. Did you stay with me or did I lose you? Amal, how are you doing? Are you really?
So z is 0 to that function?
Z would be 0 to that function, y would be 0 to its function, x would be 0 to its number. Yes. Because that's why we're doing first octant. If you can do first octant and use symmetry, life is so much easier because then all your bottoms are zeros.
Could you also just do like z equals 0 and half if it's like not
I'd have to see the problem we're talking about. There will be more symmetry. So, but yes, this has total symmetry. Laura, what was your question? So since your outer integral is always just going to be numbers, right? But your y, if you were to go x 0 to 2, if I went y 0 to 2, then what I'd end up with for my bottom region would be a rectangle, right? and it'd be a rectangle being plugged into my z function. So what I'd end up with is I'd end up with positive z's for the part that's inside and like weird negative z's for the part that's out. I don't know what I get for the part that's outside. I'd get undefined points for the integral we get.
What? How do you solve the integral?
I'm sorry. I talked you through it, but I didn't actually show you. So there's your integral. Bye guys. Wow, that class went fast. There's no function. Volume, if you do dx, dy, dz, right, there is no integrand. This is your 3 dimensions.
How about for the previous problem?
The previous problem wasn't finding volume. It was just practicing doing triple integrals. Okay?
I understand it here, but then I'm gonna go on, and it's like, what?
Your homework, I looked at your homework tonight. It's really not bad.
It's always like this is like when you had juniors, and then the homework is Sunny Switch for SpongeBob.
That's so true. It's so much harder.
Yeah.
Really?
Like this is when you had juniors.
Okay, so,
It feels like
oh my gosh, we didn't get to the David James slide. Oh, I have to show you this tomorrow.
Let's read about the Zoe Yang slide. Let's get a sneak peek because we say.
Do you want to sneak
Wait,
peek?
isn't there no integrand, just one?
Yeah, because volume is all taken care of by your z's, your y's, and your x's. When you have no integrand, that's what you get with volume. That's how you get volume.
we don't know why.
Basically, you can just drop that third integral bracket and break it down.
Exactly.
So
That is exactly true. Yes, you could just do the double integral, put this in down here as the integrand, and you'd have the exact same thing.
Wait, see, the
Oh, okay. So why would you just solve for the double?
You could, except we're learning, this is our intro into triple integrals. Yeah.
I like weirdly understand this really well, but then like with the two
I don't
I'm like
stop, like-
confused with boundaries and stuff.
We need to do more.
Yeah, and like homework is not helping me. It just takes me like a really long